Greetings and welcome to the Problem Set 2 video, which will hopefully help you to learn the material, get unstuck when you get problems and stuff like that. Hopefully this will be a pretty cool time. Like the video for Problem Set 1, this is not a video that I'd recommend watching from start to finish, but kind of skip around, all right? If you've tried the problems ahead of time, which I do recommend, you can then skip forward to the particular problem you want me to explain, and you won't have to watch the other ones, which are probably pretty boring. So definitely feel free to move around. You will need a periodic table. I recommend the mhchem.org/per tab version. That's a really great periodic table that we'll be using this whole quarter. If you need additional assistance outside of this video, definitely feel free to contact me. Mike.russell@mhcc.edu works really well. Email. You can also talk to the MHCC LSC/Avid Center located above the library on campus or through the website mhcc.edu/LSC. They have people there that will help you with problems and stuff like that, no problem. But without further ado, let's get into the problem set video and we'll see how to do these different problems. On the basis of the formula, classify each of these substances as an element or a compound. So a compound is a mixture of elements, and an element is something found on the periodic table. So during this problem set, I highly encourage you to have a periodic table in front of you. If you look on the periodic table, you will see entries for aluminum, and you'll also see an entry for nitrogen. But if you have two species together, then it's going to be a compound. So ALN, the name of which would be aluminum nitride, would be a compound. And the next one, CO2, is also a compound. It's a mixture of carbon and oxygen. But you can see that this last one, it's a big C and a little O, and that's cobalt. And that's all by itself. All right, there's nothing else with it. So cobalt is an element. All right, now if we would have written that as capital C, capital O, it would have been a compound. It would have been a carbon and oxygen compound, carbon monoxide, but CO by itself would be an element. So compounds can be broken down, at least in theory, into their elements, but elements are kind of like the building block. That's kind of the idea here. Let's use the terms proton, neutron, and electron to classify each of these different pieces, all right? So we'll go through and kind of figure this out. So has no charge. Well, if you look at all three of those, the neutron is the one that doesn't have a charge. Neutral, neutron, all right, yeah. Okay. The next one has a charge equal to but opposite in sign of the electron. So if the neutron is neutral and it's opposite to that electron, then probably, of course, it's going to be a proton, and that's what it is. Protons and electrons have a charge. Protons are positive and electrons are negative. The charge can be measured. And protons and electrons are opposite, but equal in magnitude. So that's why we refer to protons as +1 and electrons as -1. C, not found in the nucleus, that's going to be the electron. Protons and neutrons are found in the nucleus, and electrons kind of circle around the outside. We'll talk more in a future problem set about where the electrons are and what they're doing, but they aren't in the nucleus. And then finally has a positive charge. Yeah, you got it. It's the proton, all right? So pretty straightforward, but it's good to know these different materials in the atoms and what they're made of and what they can do. Let's see if these statements are true or false. So A, the nucleus accounts for almost all the volume of an atom. That is false. The nucleus has most of the mass of the atom. Protons and neutrons are both about 1 atomic mass unit, and an electron, it's something like 1/2000th the mass of protons and neutrons. Very, very small. The nucleus has most of the mass. Most of the volume is in the space the electrons circle around. So that's the difference between those two. B, the nucleus can be positively or negatively charged. Let's stop right there. We saw that electrons circle, quote unquote, around the nucleus, and electrons are negative. So the nucleus can only be positively charged. That's false, all right? Nucleus is always a positive space to be in. C, the nucleus of an atom contains an equal number of protons, neutrons, and electrons. That's false, all right? Most atoms have more than one isotope, all right? And sometimes you'll have one isotope where the protons, neutrons, and electrons are equal. So, for example, carbon-12 would be a good example of that. But there's all other kinds of nucleus and stuff that can have different combinations. So you can have, for example, carbon-13, which has 6 protons, 6 electrons, but 7 neutrons. So most of the time, they will not be equal to each other. And then finally, the nucleus of an atom is always positively charged. Yes, that's true. Protons, which are positive, and neutrons, which are neutral, exist in the nucleus. So that's going to be positive. That's going to be true. Always going to be positive. Let's figure out the right symbol for atoms with these sets of subatomic particles. All right, so in the system, Z right there, Z, that's the atomic number, and that represents the number of protons. And the A right there, A represents the mass number, and mass number is protons plus neutrons. All right, electrons, we're going to see, are going to influence the charge on the atom, and that's actually something that would go in the upper right-hand corner of that little symbol, which is not something we're talking about right now. So on this problem, we're mostly interested in the protons and the neutrons. The protons will be the lower left number, and protons plus neutrons will be the mass number, the upper left-hand number. So as an example of that, the first two, you can see that the first one had 4 protons, and that's where the 4 comes in right there. And then if you add 4 protons to 5 neutrons, you get the 9 right there. So the numbers would be 9 on the top, the protons plus neutrons, 4 protons on the bottom, and then finally the symbol comes from the periodic table, and you use the lower left number, the atomic number, to do that. So atomic number 4 is beryllium, and beryllium is always number 4. And you can hopefully see the same thing on the second one too. 7 protons, so we have an atomic number of 7. And 7 protons plus 8 neutrons, 15 is the mass number. And 7 goes with nitrogen, nitrogen goes with 7 if you look on the periodic table. And the last two are very similar. C has 15 protons, so it's phosphorus. And 15 plus 16, 31 is the mass number. And the last one, 20 protons, so it's calcium. 20 plus 28 neutrons would be 48, the mass number. Let's figure out the number of protons, electrons, and neutrons in each of these atoms. All right, so the lower left number is going to tell us how many protons there are because that's the atomic number. So in the first one, 17 is going to be the number of protons. And really, we could use the element symbol to look that up on the periodic table too. It's no problem. Now, electrons, we're going to assume that these are neutral atoms. So if there's 17 protons, there would be 17 electrons. And then finally, if you go 35 minus 17, that's going to tell you the number of neutrons. And I believe that's 18. Yes, good. Oh, good. My spur of the math moment is working okay. Anyway, so in this problem, assuming this is a neutral atom, 17 protons, 17 electrons, 18 neutrons. The 17 is the lower left number. A neutral atom has the same number of electrons, and top number minus bottom number, 35 minus 17, gives you the 18 neutrons we're looking for. So for the next problem then, you would have 25 for the number of protons there on manganese. That would mean 25 electrons, and 55 minus 25 would be the number of neutrons. That's going to be 30. So 25 protons, 25 electrons, 30 neutrons. And the same thing for the last one. So the next one would have 53 protons and electrons, and 127 minus 53, or 74 neutrons. And the last one, the bismuth, would have 83 protons, 83 electrons, 209 minus 83, 126. I didn't know that one off the top of my head. Anyway, 126 neutrons in that system. So you can see how on the symbolism, the lower left number is the number of protons. That equals the electrons if it's neutral, and usually these questions are. And then finally, neutrons to get them top number minus bottom number. For this problem, we're going to look at different isotopes of strontium. And let's talk about that for a minute. So first of all, what we're talking about in this problem are 4 isotopes of strontium, the same element. Strontium on the periodic table is number 38. And so 38 is what goes in that little Z part right there. So all of these things we're going to talk about in this problem, they're all going to have a 38 because they're all strontium, all right? What's going to differ is the top number, the mass number. Now, the first one it claims here is 84. So the first of these isotopes, we would have an 84 on the top, a 38 in the bottom, and X, the symbol would be SR. And again, the symbol comes from the periodic table number 38. The other ones then, we would just add 2, 4, or 5 more to 84. So for example, the second one then would have 84 plus 2, 86 for the top number. So we'd write 86, 38 SR. The next one would have 84 plus 4, 88. The next one would have 89. So here's the way that chemists would write the symbols for these. And you can see the lower left number is always 38. It's always strontium. But what differs then is the top number, the mass number. And we're going to use then protons plus neutrons to figure that out. Each of these elements have only 2 naturally occurring isotopes. And in each case, we want to predict which isotope is more abundant, all right? Like which one of these is more likely to happen. And at first this question might seem a little weird, but if you think about how this works out, it's not too bad. The key to figuring out what's happening here is to have a periodic table in front of you. So for example, on the first one here for boron, all right, we've got boron 10 and boron 11. And at first you might think, man, I don't know which one's more abundant, but look at the periodic table and the atomic mass of boron, which is the other number on a good periodic table. It'll always have the 5, all right, but it should also have 10.811. Well, if you take 10.811, which is on my periodic table, and you round it up to 2 sig figs, it's going to be closer to 11 than it is 10. So I would predict that boron 11 is closer or more abundant in mass than boron 10. This is all about averages, okay? And if you have 2s and 3s that you're trying to find the average, if you have a lot more 3s, the average will be closer to 3. If you have a lot of 2s when you're trying to average, it would be closer to 2. In this problem, we're kind of figuring out the average between 10 and 11. And this number on the periodic table, if you tells us that 11 is more abundant than 10. But all you really have to do is round up, all right? Round up to the nearest number of sig figs, and you should be okay. So the next one, knowing that, gallium is about 69.723. And again, every periodic table is a little bit different. But 69.7, all right, is, if you look at it, 69 and 71. Now, if we round up here, we get 70, and that's halfway in between, so that's not very handy. So let me use another trick. 69 and 71 are on the periodic table, and 70 would be right between. So in the old days, maybe in grade school or something, you saw a number line, and 71 was there and 69 was there. Well, the mass on the periodic table, which is 69.7, right about here, all right? It's not quite 70, and that's important for us. So you can see that 69.7, if that's the average of all the galliums, 69.7 is closer to 69 than it is 71. So I would predict, based on this information, that 69 is more abundant, and it is, all right? If you have 69 and 71, the halfway point would be 70, all right? That would be 50-50. But we don't have a 50-50 thing. It's 69.7. And 69.7 is closer to 69 than it is 71. So again, this number line thing works really well for me. I can use that sometimes to figure out which one is more abundant, and you can too. Now, silver is the next one, 107.8. Again, if it was 50, 107, and 109, then that number on the periodic table would be 108, but it's 107.8. That's closer to 107 than 109. I would call silver 107 more abundant. And then finally, for thallium, which is, by the way, a nasty poison, pretty crazy. Anyway, thallium, if you look on the periodic table, thallium is 204.38, all right? And 204.38 is closer to 205 than 203. I would predict thallium 205 is more abundant. So don't be afraid to use number lines, rounding up in the case of the first one, whatever you need to do to figure it out. But it is a nice way to make a prediction as to which of these is more abundant. This problem, we know that copper has two main isotopes, copper-63 and copper-65, and we want to calculate the atomic mass of copper based on that. And notice we have the abundances there. Copper-63 is 69% roughly, and copper-65 is about 31%. So this is what chemists do when they figure out the numbers on the periodic table. Now, if you look at the periodic table, copper is 63.546. So 63.5 is closer to 63 than it is to 65. But this process we're going to use here is how they do it. And in statistics, we want to take the decimal version of these percentages and multiply it by the masses. And then we'll add those two together to figure out what the average mass is, which is really what the atomic mass is. So mathematically, here are the decimal percentages. So 69.09 becomes 0.6909, and we're just going to multiply it by the mass of the copper-63. And then here's the other isotope, 0.3091, as a decimal multiplied by its mass. Add them together into 4 sig figs, which is all we can report with these numbers. 63.55 is the atomic mass. Now, in my periodic table, it lists 63.546. The scientists that made that number had a few more sig figs to work with than we do, but the process is the same, all right? It could also be that there's other isotopes of copper that make it 63.546 and not 63.55. But either way, I hope you get an idea. It's not magic how they get these numbers. It's just using the data available to you, finding a good answer based on your sig figs. Now we're going to start getting into a little bit of naming. So let's name these compounds. These are fixed charge binary ionic compounds. So fixed charge means that we know the metals, and they're metals because ionic compounds always have positives and negatives. And we can do this, and we can do it without transition metal variable, the Roman numerals used in transition metals. So we won't need any of those here. Also, because they're ionic, we won't use Greek prefixes. Greek prefixes are for nonmetals. So naming these is pretty simple. It's the name of the metal and the nonmetal with an IDE ending. So the first one, beryllium sulfide. The second one, that Ga is gallium, and Cl would be chloride. So it'd be gallium chloride. And the last one, calcium oxide. So naming these is pretty simple, all right? Metal plus nonmetal as "-ide", don't need to add Roman numerals, Greek prefixes, anything like that. Pretty chill. In these compounds, we have a variable charge metal, and you can see that because there's two combinations listed. So for example, in the first one, Sn is 10. 10 is there, but chloride, first one has 4 chlorides and the second one has just 2. So for these, we're going to need a Roman numeral next to the metal. Tin and iron in the next one and gold in the last one are all example, or gold and silver, excuse me, in the last one. Those are all examples of metals where there could be more than one charge. Now, the key to figuring out what the number is on the metal is through the nonmetal. So, for example, in A, chloride is always -1. So in SnCl4, that means 4 -1 chlorides. And that tin is going to have to balance it with a +4 charge. All of these compounds going to have equal positives and negatives. So the first one would be a tin 4 chloride, where the 4 represents the charge on the tin. No problem. And the second one, because again chloride is -1, but there's only 2 of them this time, that would be tin 2 chloride. So you'd write that out like this. The Roman numeral, again, is the charge on the metal. First one would be tin 4 chloride. The next one would be tin 2 chloride. And we're using the nonmetals to figure that out. On the next one, it's iron. So they're going to be iron sulfide compounds, but we need that Roman numeral to tell each other which it is. So again, like on the last one, the nonmetal is the key to figuring this out. So sulfur is in group 6. It's a nonmetal. So 6 minus 8, sulfide is going to have a -2 charge. The iron is going to balance that in FeS with a +2 charge. So the first one, FeS, we would put Roman number 2 sulfide, or as I would call it, iron 2 sulfide. On Fe2S3, you have 3 -2 sulfurs, so that's -6 from those. And the 2 irons are going to balance that with a +6. And so if you have a +6 overall and 2 irons, that means each of those irons is a +3. So the second one is going to be iron 3 sulfide. So we'd write that out, iron Roman numeral 2 sulfide, or as I'd say, iron 2 sulfide. And the other one would be iron Roman numeral 3 sulfide. Again, where that Roman numeral is the charge on the metal. Now, the last one, we've got a gold and a silver. And I put this in here because gold and silver are really easy to confuse. But the first one is gold. Iodide is -1. So the first one would be gold 1 iodide. The gold is +1 to balance the iodide's -1. The next one, actually, silver. Silver is one of the stairs. So technically, silver is not a variable charge metal. So the next one, you could just call silver iodide. You don't really need the Roman numeral. If you did put it there, it's not the end of the world, because silver does have some strangeness once in a while. But in the rules we're using here, really, silver is a stair, one of the stairs, so you wouldn't need a Roman numeral. So technically only the first one you need it, gold 1 iodide, second one silver iodide. Cool. Polyatomic ions are going to be really important to us. Poly means many, many atomed ions. So if you see some of these, just realize there's going to be more than one atom, and they all stick together with an overall negative charge, at least usually. One of them's positive, but most of them are negative. A lot of times, but not all the time, they'll have an ATE or an ITE ending. So that means you've got a complex with oxygen. And you can see that in this one, it sounds kind of like nitrogen. So these are going to be nitrogen compounds with oxygen in them and some kind of overall charge. Now, by hook or by crook, you must learn what these are. And in the notes, there's a thing about Nick the Camel, and you can use that to figure it out. You can also just go through and memorize what they are. But nitrate and nitrite, nitrate is NO3 minus 1, and nitrite NO2 minus 1. So again, you can at least figure out that they have nitrogen. 8 and ite will mean oxygen, but figuring out the numbers of oxygens is something you got to figure out. And then the negative one is also cool. Now, nitrite, ITE, ite has less oxygens than 8. So you can see how 8 has one more oxygen than ite. All right, that's another kind of a relative trick you can use as well. The next ones both have a chlor, so that's chlorine, but you can see that they're both ATE, so they're going to have oxygen. The second one has a per in front of it. Per means one more oxygen than the regular version. So we know that the perchlorate will have one more oxygen than the chlorate. So again, you've kind of just got to know these, figure them out. Chlorate is ClO3 with a -1 charge, and perchlorate, one more oxygen, ClO4 with a -1 charge. And again, you kind of got to just figure these out. Phosphate and phosphite, phosphorus is the key, is the central atom. And ate and ite means, of course, there's going to be oxygen. Now, notice how the last examples, nitrate and chlorate, the ates had 3 oxygens. And I'd love to tell you that phosphate with an AT ending had 3 oxygens too, but that's not the case. The most common form of the polyatomic ion is the one that gets the ATE ending. And several of the AT endings don't have 3 oxygens, they have 4 oxygens. So phosphate is PO4 with a -3, and phosphite still has 1 less oxygen, PO3 with a -3 charge. So please realize that, yeah, phosphate and phosphite, the ate and ite pattern does follow, but ATE does not necessarily mean 3 oxygens. Phosphate and sulfate are both examples of polyatomic ions with 4 oxygens instead of 3. So again, memorize them, use Nick the Camel, whatever you need to do. These are going to pop up a lot. And I apologize as your instructor for saying memorize things, because I honestly don't like memorizing things, but I don't know of a better way to do it. So alas, fascist chemistry, whatever you want to think about. Here's a question. It says, which in the following pairs, which ones are polyatomic ions present in both members of the pair? All right. So basically it's saying in the compounds listed, do both of the compounds have a polyatomic ion? Let's look at A. Calcium sulfate, the second one, SO4, is a polyatomic ion. All right, it's SO4 with a -2. The calcium is there to balance it. So this one definitely has a polyatomic ion. It's got sulfate. However, notice that this compound has calcium, it has sulfur, and oxygen. It has 3 types of atoms in it. All right, you must have 3 types or more of atoms to have a polyatomic. And if you didn't know about SO3, notice how SO3 has just 1 sulfur and 3 oxygens, or 2 types of atoms. So A does not have a polyatomic ion. All right, A is sulfur trioxide, which is a nonmetal and a nonmetal coming together, while the second one is calcium sulfate. It does have the sulfate. So the first one, we would say no. The first one, SO3, does not have a polyatomic ion. Those are neutral. They have the sulfur and oxygens are getting together. There's no charge. In the second one, sulfate, you definitely have a charge. Now on B, we don't have that problem. The first compound has nitrogen, hydrogen, and bromine, 3 types of atoms. You bet that's going to have a polyatomic ion. And the second one, potassium, chlorine, and oxygen, yep, that's going to have one too. So on B, both of them do have a polyatomic ion. In B, the first one, the NH4, is ammonium. It's a positive polyatomic, one of the few positive ones that we'll deal with a lot. In the second one, it's the ClO-, that's called hypochlorite. That's the polyatomic ion that you see in that one. So look for 3 or more atoms to distinguish if you have polyatomic ions in a species. So let's name these compounds. These have polyatomic ions in them, so we're going to have to be careful of that. Also know that in this problem, we have copper in the first one and lead in the second one. So copper and lead are both variable charge metals. So that means we're going to need a Roman numeral associated with it. So again, you've kind of got to know the polyatomic ions. NO3 is -1. It's nitrate. And if NO3 is -1 and there's 1 copper in the first one to balance it, this first one is going to be copper 1 nitrate, where the 1 is the Roman numeral. The second one is going to be similar, except now you can see there's 2 nitrates, all right? And if you have 2 nitrates, that means you're going to have -2. The copper is going to balance it. That one's going to be copper 2 nitrate. So again, nitrate's -1. The first one would be copper 1 nitrate, and the second one, copper 2 nitrate. The next two have phosphate, and phosphate is a -3. So in the first one, the Pb3PO42, and by the way, notice how more than one polyatomic you do use parentheses, but if there's only one polyatomic, you don't put parentheses, and that's really important. But anyway, back to your regular scheduled programming. Back to Pb3PO42, we have two -3 phosphates, so that's -6, and the 3 leads are going to balance that with a +6. Once in a while, I'll try to do this kind of thing where I'll write -6, which is -3 times 2 to get that -6, and then the leads are going to balance it with a +6, but there's 3 of them. So that means that each of the leads in the first one is lead 2. So the first one is going to be lead 2 phosphate. The next one, we can do the similar kind of thing. We've got 4 -3 phosphates. Wow. So that's -12. And that means that those 3 leads are going to balance that with a +12. 12 divided by 3, that's a +4 lead species. So the second one is going to be lead 4 phosphate. So again, the first one there is lead 2 phosphate. Sorry, I kind of wrote over it. And the second one would be lead 4 phosphate. So you've got to know that phosphate's -3, and the positives will balance the negatives to figure it out. You got this. These compounds are binary molecular compounds, and what that means is that they have covalent bonds. And in covalent bonds, we can use the Greek prefixes to describe how many atoms there are. If the first atom listed is by itself, you don't use a Greek prefix, but basically every other time you do. Like the previous examples, the second atom listed will get an IDE ending. So what this means, the first one, 4 sulfurs, that would be tetrasulfur, and 2 nitrogen, but we're going to turn nitrogen to nitride. That would be a dinitride. So the first one would be tetrasulfur dinitride. Okay, so Greek prefixes on everything unless the first one is by itself, and the second atom always gets an IDE. The second compound there, SO3, which we saw earlier, which was not a polyatomic ion, sulfur would be the first one. And if the first one's by itself, you don't call it mono. The second atom always gets a Greek prefix, but the first one, in this case, we don't. Sulfur, tri for 3, trioxide, sulfur trioxide. Sulfur trioxide is a precursor to making sulfuric acid, but that's nothing important here. In this problem, we're going to take the names and turn them into formulas. And you can see lots of Greek prefixes here, so that you know that in these cases, they're all going to be nonmetals and nonmetals. You wouldn't put Greek prefixes with any of the metals. So di is 2. Disulfur would mean 2 sulfurs, and monoxide, which is like monooxide, would be a single oxygen. So S2O would be the formula here, and we're good to go. The second one, tetra, is 4 for phosphorus. Hexoxide, which is like hexaoxide, but people usually kick out double vowels. Hex is 6, and oxygen, of course, is O. This should be P4O6. And then the last one, the most famous probably of all of these compounds, arguably, carbon is by itself, so 1C. Dioxide means 2 oxygens, CO2. So that's the formula for carbon dioxide. These are all acids, and naming them and turning names into formulas is going to be more and more important as we go along. These are all combinations of an acid with a chlorine, and you can see what changes is the number of oxygens. We have no oxygens in the last one, and the top one, A there, has, of course, 4 oxygens with it. And there's kind of a pattern that goes along with these. In this case, it's nice to know what the base of all of the chlorine oxygens is. And so I'm going to give you not only the first one, but the second one. When it comes to the polyatomics, the most common of these is ClO3, which is chlorate. And chlorate, if it's an acid, i.e. add an H plus to it, becomes chloric acid. So all of the chlorine oxygen acids are based on the base unit, they call it. And one more oxygen, like in the first one, you would add a per prefix to it. So if HClO3 is chlor, which is from chlorine, and then ic acid, you can see hopefully how HClO4 with one more oxygen is also an ic acid, but it's a per ic acid. So per chloric acid. If you had a bromine in the middle, it would be per bromic acid, and HBrO3 would be bromic acid. So you need to know the base, and then the prefix and or suffix helps you with the rest. Now, HClO2 has one less oxygen than HClO3, the base. So you turn the ic acid into an us acid. So the next one would be chlorous acid, OUS acid. And that tells you you have one more less oxygen than the common form chloric acid. The next one has even one less oxygen, so you put a hypo in front of the chlorous acid on that one. D is hypochlorous acid. All right, so one less oxygen means that you put a hypo in front of it, hypochlorous acid. So again, on C, you change the ic acid to the us acid, and on D, you still have the us acid, but now you also add a hypo. Finally, if you have an acid without any oxygen, it gets a hydro prefix. So HCl, which is by far the most common probably of all of these, would be hydrochloric acid. And hydrochloric acid is the hydro tells you you don't have any oxygen by it. It's a good idea to figure out how this works. It's not super exciting, but knowing the different acids can be really helpful later on. This problem, we're going to calculate the molar mass to 0.01 grams per mole for each of the substances. So before you start this problem, make sure you have a periodic table and that at least most of the periodic table entries go to 0.01. This process is not hard. It's a little tedious, but we're going to go through the steps how you do it. Under sodium on the periodic table, you should have a number to 0.01. It's like 22.99, depending on your periodic table, something like that. You're going to add that number to a hydrogen, which is about 1.01, and a carbon, which is about 12.01, and 3 oxygens, and each oxygen is about 16. So sodium plus hydrogen plus carbon plus 3 oxygens. Here's what I did when I figured it out. And you can see here, okay, so on my version, my periodic table was 23.00. That's fine. Add that 1 sodium. There's 1 hydrogen at 1.01, 1 carbon. And you can see here how oxygen was multiplied by 3. Anyway, if you take all of those numbers and you add them up, it comes out to be 84.01. And that's the molar mass of sodium bicarbonate, which is really baking soda. You might have this in your house right now. But anyway, woohoo, you just figured it out. Now, if you have 84.01 grams of baking soda, that means you have a mole of baking soda. And remember, a mole of anything means 6.022 times 10 to the 23rd molecules. So if you would weigh out 84.01 grams of baking soda, you would have 6.022 times 10 to the 23rd molecules of it, which is kind of crazy. The next compound, thallium-1 sulfate. It's a poison, all right? It's supposed to be for rats and ants, stuff like that, but sometimes there's some forensic studies. I believe they're using thallium-1 sulfate to figure it out. Nasty, nasty stuff. Anyway, same idea on this problem like you had on the last one. In B, you're going to have 2 thalliums. You'll add that to 1 sulfur and 4 oxygens. And again, all these numbers you can look up on the periodic table. You certainly don't have to memorize any of them. You could tell that even I get the numbers wrong sometimes. But anyway, if you add these all up, 2 thalliums, and thallium's pretty big, plus the sulfur plus 4 oxygens, add them up, 504.82 grams per mole. If your numbers were a little bit different than mine, it's probably okay. Periodic tables do tend to vary a little bit in their atomic masses. So if you have some different numbers quoted there, your numbers will be a little bit different. different, and that's okay. Hopefully it's different in the last digit, the hundredths place. So maybe on sodium bicarbonate, you might have 84.00 or 84.02. That's the doubtful digit acting up. In science and measurements, the doubtful digit is always uncertain. But anyway, just be aware that periodic tables do have some differences, and it's okay. Another hint for this section, we're going to do a lot of molar mass calculations in this class, and it's really cool if you can find either online on a website or an app for your phone a molar mass calculator. And I have both. I have websites I use, and I have a molar mass calculator on my phone, and it's easy to just put formulas in and get these numbers. And there's nothing wrong with doing it manually by any means. However, when you're doing a lot of them, it does save some time, so it might be worth your time to check it out. Here's some compounds, naphthalene and sodium cyanide, and what we want to do is we want to find the percent element composition for each of them. So what that means, for example, for naphthalene, we want to find the percent carbon and the percent hydrogen. And on sodium cyanide, we want to find the percent sodium, percent carbon, and percent nitrogen. These aren't too hard to do. The first thing you need to do is you need to find the molar mass. And again, like it says right there, I would find the molar mass to 0.01 grams per mole. Then, whatever the molar mass is, that number is going to go on the bottom. And if you wanted to find, for example, in the first one, percent carbon, you would put the carbons only on the top. So for A, you would go 10 carbons times 12.01, which is the mass of carbon. That number is going to go on the top, and the total molar mass goes on the bottom. So for naphthalene, this is what you want to do. And again, the first part, you've got to find the molar masses of these compounds. And again, if you've got the molar mass calculator, like we talked about in the last problem, good for you, put them in fast. On the other hand, you can calculate yourself, which is totally fine. Anyway, naphthalene, molar mass, 128.18. So when you're doing, for example, percent carbon, the 128.18 goes on the bottom, and the amount of the carbon goes on the top. So 10 carbons, 10 times 12.01, that goes in the top. Molar mass of the whole thing on the bottom. This comes out to be 93.70% carbon. A lot of carbon in naphthalene. Now, hydrogen, amount of hydrogen in the top, so 8 hydrogens times the molar mass of hydrogen, 1.01. But again, notice we're dividing by the molar mass again, times 100%, 6.30% hydrogen. If you've done these calculations right, all of the percentages together should be about 100%. This time it's exactly 100%, so that makes that pretty easy. 93.70 plus 6.30 is 100. That's good. All the percentages together should be 100%. If it's like 99.99 or 100.1, again, that's not the end of the world. The doubtful digit is acting up on us all the time, but it should be about 100%. So the next problem, sodium cyanide. Let's do the same thing. First, find the molar mass, a sodium, a carbon, and a nitrogen. And then the percentages will be just like 1 sodium divided by the molar mass times 100 for percent sodium, etc., etc. So here's the work. Molar mass again, 49.01. And you can see that I divided by that number in each of those percentage calculations. And then in the top, you just put 1 times the molar mass of that, 46.91 plus 24.51 plus 28.59 comes out pretty close to 100%. Life is good. So again, if you're asked to find percent composition or percent element or something like that, molar mass on the bottom and the amount of the element you're using goes on top. Let's figure out the number of molecules or atoms present in each of the following. Now, anytime you're trying to find molecules or atoms, that's when Avogadro's numbers is going to kick in somewhere. And if you have the moles like you do on the first one, moles times Avogadro's number is going to give you the answer. So on the first one, 4.69 moles, we're going to multiply that by Avogadro's number, 6.022 times 10 to the 23rd. That's going to turn moles of CO into into molecules of CO. And it says you have to find molar mass. On this one, I'm sorry, really you don't have to find molar mass, so sorry about that. So on this one, what I intended anyway, you can see here how 4.69 moles of CO times Avogadro's, you get this massive number right here. That's the molecules of CO. If you did find the molar mass of carbon monoxide, it's about 28 grams per mole, but really you don't need it here. So sorry, that was me being a little extra zealous. However, on the second one, B, we will need the molar mass of the element. Notice in the second one, we're starting with grams. And Avogadro's number allows you to go from moles to molecules, or atoms in the case of lithium, but we have to get to moles first. So on B, we will have to go grams to moles first, and then we can use Avogadro's number to find the number of atoms. And by the way, CO is a compound, so that's why we're using molecules. But on the second one, lithium is an element. The smallest piece of an element is an atom. So the second one, we're going to find atoms. Anyway, backing it all up, grams to moles first for lithium, then moles to atoms using Avogadro's. Lithium on the periodic table, 6.941. That's 6.941 grams per mole. We're going to divide by that number to get rid of the grams. Then we've got just moles left over. Then finally, we'll multiply by Avogadro's number. Moles will cancel. We'll have nothing but atoms left over. And you get the massive 3.255 times 10 to the 23rd atoms. That is a lot of atoms. But anyway, it's kind of cool how math here allows you to calculate that without going through and physically counting something, which would just take forever. Let's calculate the mass in grams of 0.981 moles of each of the following. So we're going to go from moles to grams. So we've got 0.981 moles of SO2. How many grams is that? We will need the molar mass on this one, definitely. Because if you're going from moles to grams or grams to moles, that's when the molar mass is helpful. So either using your molar mass calculator or using the periodic table, you would add up 1 sulfur and 2 oxygens. Sulfur is about 32 and oxygen is about 16, so it's going to be a number around 64. That's not a very good sig fig answer. You can do better on your calculator or the periodic table. When I used a better table, I got this number, 64.06. That's the molar mass of SO2, grams of SO2 in a mole. So moles of SO2 times grams per mole. You can see how the moles cancel out. We've got just grams, 62.8 grams of SO2. So if you had 62.8 grams of SO2, you would have 0.981 moles of SO2. We're going to do the same thing on the second one, that tetrasulfur tetranitride thing. We've got to find the molar mass, all right? So 4 sulfurs and 4 nitrogens, add that up to get some number, and then 0.981 times that number will give us the grams. So when I did that problem, I got 184.28 grams per mole. 0.981 times that number was 181 grams of S4N4. I'm rounding up to 3 sig figs, 180.77, etc. is rounded up to 181. Cool. Here are 3 compounds written as a molecular formula, and I'd like you to tell me what the empirical formula is. Now, an empirical formula is just the smallest whole number ratio of atoms, and whole number is key. You don't want to go down to fractions, all right? Chemists usually hate fractions. So, for example, in the first one, AS4O6, if you divided the 4 and the 6 by 2, you'd end up with a ratio of 2 AS and 3 O's. AS2O3 would be the empirical formula. So for the first one, AS2O3 would be right. But the second one, though, PB3S4, you can't divide those by any number and end up with something other than a fraction. So because we can't end up with anything other than fractions, PB3S4 is the empirical formula and the molecular formula. But C4H8, you can divide both of those numbers by 4. You'll get 1 carbon, 2 hydrogens for an empirical formula of CH2. Mass percentages will lead to an empirical formula for a compound. It doesn't necessarily give you the molecular formula, but it can give you the empirical formula. So let's look at how you would do that for this combination of elements. We've got a compound which is 47.26% copper and 52.74% chlorine. And the question is, how do you get to the empirical formula? Remember that every formula, H2O, CO2, NaCl, it's a ratio of moles. So any formula you can think of, CO2, H2O, NaCl, it's a ratio of moles. So we have to somehow get those percentages into moles. So what I would do here is I would first turn those percentages into grams. Let's assume we have 100 grams of this compound. That would be 47.26 grams of copper and 52.74 grams of chlorine. And once we have those masses, we can turn the grams into moles using the molar mass, and we'll compare the moles then to see what the ratio is. So for CO2, we'd end up with 2 moles of oxygen for every 1 mole of carbon, for example. That's what we're going to do here. So percentages to grams to moles to the comparison part. So in 100 grams, we're going to have 47.26 grams of copper. That's just direct from the percentage, and 52.74 grams of chlorine. Next, what we'll do, we'll take those grams, turn them into moles, and then we'll compare the moles. So this first part right here, we're calculating how many moles of copper and chlorine there are. So you can see, like, here's 47.26 grams of copper. Copper is 63.546 or so on the periodic table. I rounded to the hundredths, which is fine. The grams of copper will cancel, and we'll have then moles. So 47.26 grams of copper represents 0.7437 moles of copper. And you can do the same thing for chlorine. Chlorine is 35.45 grams per mole in the periodic table. So that comes out to be 1.488 moles of chlorine. Then those two numbers actually represent a really sloppy formula. Like it could be Cu.7437. My thing is not writing very well. Cl 1.488. But hopefully you've recognized that we've never ever had a formula of 0.7437 coppers to 1.488 chlorines. That would drive chemists crazy. So in order to get them into whole numbers, you divide both numbers by the smaller moles. So copper 0.7437 is smaller than 1.488 chlorines. We're going to divide both of those moles by 0.7437. Copper divided by itself comes out to be a perfect one. That's the idea. And the other one comes out to be almost exactly 2 to 1. Close, not perfect, but pretty gosh darn close, especially to one significant figure. So we would break this down then to CuCl2. It's 2 chlorines for every 1 copper. And that's the empirical formula of this molecule. So again, let's look at that process. Percentages into grams, grams into moles, and then compare the moles to get the empirical formula. Most of the time, when it comes to ionic compounds, the empirical formula is the absolute answer, the molecular formula, if you will. But we're going to see that sometimes it's not quite that easy. Here are some empirical formulas, and the molar mass, or the molecular mass technically, is given as well. And we're going to use those two pieces of information to find the molecular formula, all right, what this molecule, quote unquote, looks like in space. So let's look at the first one, Cb2H3. That could be the formula for a compound, but it also could be just an empirical formula. So it's possible that the molecular formula for the first one is Cb2H3, but it could also be something like C2B4H6, or it could be C3B6H9, all right? Some integral of Cb2H3. And how we're going to figure out which of those answers is correct, we're going to compare this number, the molar mass of the whole thing, or molecular masses, which again is same number, just different units. We're going to compare that to the mass of this part by itself. So what we're going to do here is we're going to add a carbon, 2 borons, and 3 hydrogens together. And that's going to give you some number. If that number happens to be 73.3, then empirical formula and molecular formula are the same. If it's not 73.3, then it's going to be some whole number ratio of 73.3 divided by the actual number. And we're going to use that to find it. Let's look at how this works. 73.3 is the molar mass of the whole compound. And if you add up a carbon, 2 borons, and 3 hydrogens, that's where this number came from. Now, carbon on the periodic table, about 12 grams per mole. Boron, I think, is 10.8 or so times 2. And hydrogen, 1.01 times 3. You add those 3 things together, and that's where this number comes from. So because molecular, the empirical formula's molar mass is different than the molecular formula's molar mass, we need to find a ratio. So notice here that you take the number that was given, put it in the top, and this number is going to go in the bottom. And you should always get a whole number ratio here. And in this ratio, you can see it comes out to be 2.00. So we're going to take the empirical formula twice based on this ratio. So that means that the molecular formula of the whole thing is twice the empirical, or C2B4H6. So again, how this worked, we figured out essentially what the molar mass was of this thing right there, and that came out to be 36.66. We compared that to the molar mass of everything, 73.3, came out to be a whole number ratio of 2. And they'll always be whole number ratios, by the way. That 2 will multiply by the empirical formula to get C2B4H6, the molecular formula. And C2B4H6 is kind of like the holy grail of these finding them out. On the next one, we're going to do something very similar. We're going to find the molecular mass of C5H10O2, and we're going to compare that to the molar mass of the whole thing, which is 102. And that whole number ratio will apply to the empirical formula to get the molecular formula of the whole thing. C5H10O2 comes out to be 102.51. And again, that came from 5 carbons, 5 times 12, plus 10 hydrogens, 10 times about 1, plus 2 oxygens, 2 times about 16. And you can see that 102.51 awfully close to 102. And these ratios will always be whole numbers. So let's call that a ratio of 1. That means that the molecular formula is the same as the empirical formula. And that does happen. Remember, we saw examples where the EF and the MF were the same. Water is a good example of that. H2O has the same empirical as molecular formula. Same kind of thing. It does happen. You will, though, sometimes have ones like the first one where the ratio is not the same, but you can use the difference in the molar mass of the whole compound compared to the molar mass of the empirical unit to find out what the answer is. This last one is a great way. If you can do this problem, you've got this whole problem set down. In this problem, we have percentages. Some kind of compound has carbon, hydrogen, and oxygen. And we also have the molar mass of the whole compound. And from this information, we want to find the molecular formula of the whole shebang. And we know it's going to have carbon, hydrogen, oxygen, but of course, how many does it have in it? So we're going to use the techniques of the last several problems to do this. So what we're going to do is we're going to take the percentages and turn them into grams, and then grams into moles. We'll compare those moles together to find the empirical formula of this compound. The next step will be like the last problem we just did. We'll find the molar mass of the empirical formula. We'll compare it to 146 grams per mole, and then we'll be able to find the molecular formula from there. So what this looks like. Let's assume 100 grams total. So that means 49.30% carbon becomes 49.30 grams of carbon. And we'll turn grams into moles. 12.01 again comes from the periodic table. So that's 4.105 moles of carbon. And you do the same kind of thing for the hydrogen and the oxygen to get those numbers. Now, using those numbers right there, that would make a very crude formula. formula, but we want to kind of make it nicer. And to make it nicer, you want to divide all of those numbers by the smaller number of moles. And 2.737 is smaller than the other two numbers up there. In the next step, notice how I took all the moles and I divided all of them by 2.737. And that came out to be 1.5, about 2.5, and 1. Now, in chemistry, you have to have whole atoms. You can't have half of an atom, or 1.5, or 2.5 atoms. So that's close, but to get whole numbers, we want to multiply the whole thing by 2. So instead of having C 1.5, H 2.50, we're going to multiply everything by 2. 1.5 times 2 is 3. 2.5 times 2 is 5. And 1 times 2 is 2. So our empirical formula, C3H5O2. Now, at this level, when you're comparing moles, sometimes the ratios won't be whole numbers. We saw an example earlier of a copper 2 chloride, CuCl2, that was exactly 2 Cls for every copper. And that happens a lot of the time. But if you do see fractions at this level, you are welcome to multiply by a whole number like we did to get the whole thing. In the next part, where you take the empirical formula and turn it into a molecular formula, those ratios will always be whole numbers and you won't have to do it. But once in a while at this step you do. Okay, so C3H5O2 is the empirical formula, and we're going to now use the 146 number up there to figure out what the molecular formula is. So we're going to add up 3 carbons, 5 hydrogens, and 2 oxygens to get the molar mass of the empirical formula, and we'll compare that to 146. If the C3H5O2's mass comes out to be 146, then the empirical and the molecular formula is the same. However, if you get a different ratio, we can multiply that ratio by C3H5O2 to find the molecular formula. So the molar mass of C3H5O2 comes out to be this number, 73.08. So you would take 3 carbons, 3 times 12, plus 5 hydrogens, 5 times about 1, plus 2 oxygens, 2 times about 16, to better sig figs than I just did, 73.08 grams per mole. And you can see that is definitely not 146. So we're going to take that 146 and divide it by the empirical formula's molar mass. We should always get a whole number, and we do. It's a ratio of 2. So that means we have to multiply our empirical formula by that ratio, by 2. C6H10O4 is our final answer. That is the molecular formula for this compound. So again, to backtrack our steps, percentages to grams, grams to moles, compare the moles to find the empirical formula. And once you have the empirical formula, find the molar mass of the empirical formula, compare it to the molar mass of the whole compound. That's what's going to allow you to find the molecular formula. If you can do this process, you are good to go with this chapter, and I'll pat you on the back. But if you did have problems with it, don't feel bad. This is kind of funky. Lots of examples you can find on our website or online to help you with this process, and you can definitely email me too if you have any questions. This is something you can definitely do. You just need to practice. Okay, that's it for problem set number 2. I hope this video has been helpful to you as you learn the material, kind of see how this stuff works. This is all stuff you can do, so just keep up the good work. If you do have any further questions, don't be afraid to email me, mike.russell@mhcc.edu. You can also contact the LSC/Avid Center located above the library on the Mount Hood campus. They can help you as well. All right, good luck with your studying and have a wonderful day.